Yeah, everybody, welcome back to the webinar where today we will be taking a deep dive and looking into K-space, right? Into K-space. So this is still some pretty difficult material. I don't think it's quite as difficult as last week's. If you were to make like a graph, I think it would have been like encoding 1, 2, 3, and then K-space is kind of uh, on the downhill difficulty side of that. But it's still some pretty in-depth stuff. Next week's lecture is usually a lot easier, where we just talk about different tips and tricks about how we do things in K-space, things such as parallel imaging, um, uh, single shot techniques, how we fill K-space with MRA sequences, and so on and so forth. But this week we are going to talk about K-space, what it is, how it is filled, and this is a very, very important lecture for Physics 2. This is a very foundational lecture for what we're going to learn in Physics 2, which is the same for all the encoding, but even more so now with because in Physics 2, like I've said before, in Physics 2, what we're going to be doing is we're going to be taking all of these different things that we learned in Physics 1, and we're going to learn how we change them to create different types of pole sequences. Right? So we're going to talk about, when we talk about the fast spin echo, when we talk about gradient echoes, when we talk about MRAs, they all have different ways that they fill up K-space and take advantage of K-space. So to understand all of the different types of pole sequences we have and how they change, you have to have a good understanding of K-space to start with. Because if we talk about, okay, well, this pole sequence is different because it fills up K-space this way. Well, if you don't know anything about K-space, that makes that whole part of that lecture kind of difficult to follow. All right. So last week I would say is the hardest material, but this week I would say that this is one of the most important lectures to understand going into Physics 2. Students who struggle at the end of Physics 1 tend to have more of a problem in Physics 2. I've only briefly looked at the quiz scores that were due last night, but if you had a low quiz score from last night, I'll probably ask that you come to some tutoring, set up a tutoring session and do some tutoring just to make sure that the things that you need to understand from encoding 1, 2, and 3, that you have the basics. You don't have to understand all the details from those lectures, but you need to have a very good foundation of that encoding and K-space information, or you're going to find yourself struggling in Physics 2. Physics 2 is like the opposite of Physics 1. The first half of Physics 2 is pretty difficult, and the second half of Physics 2 is not quite as difficult. Looking at the scores in here, this class is like most classes where the first half of Physics 1 is not as difficult, but the second half is, right? So Physics 2 is the opposite. The first half of Physics 2 up to the midterm is pretty tough, and then after the midterm, it gets easier, which is the way it's designed, because with Physics 2, when you get into the second half of Physics 2, everybody here is getting ready to graduate. So you're going to start concentrating on the ART, you're going to be looking around for jobs, you're going to be polishing up a resume. So I try to, it just ends up how it ends up working is that the last couple of weeks of Physics 2 are pretty tame compared to what you're seeing now. All right. But bear with me and spend the time now, because if not, in Physics 2, you're going to be doing a lot of tutoring where we're going back over the same stuff in Physics 1. All right. So let's talk about K-space. This lecture is going to focus a lot on phase encoding gradient, right? We have the frequency encoding gradient, right? Remember, the frequency encoding gradient is what we talked a lot about last week. How receiver bandwidth, frequency matrix, and the frequency field of view all change the strength of the frequency encoding gradient in order for us to collect the echo. This week, we're going to talk about the phase encoding gradient and how it controls where information goes into K-space. Learning how we put this information into K-space explains a lot behind our parameters, especially the phase matrix. For some of you, one way that a lot of texts like to scan is by changing their phase matrix a lot. And so it's a question of, well, what's happening when we're changing that phase matrix? Some texts don't ever touch the phase matrix, right? Some don't touch any parameters. Some have other parameters they like to change, like averages and bandwidth, right? But phase matrix is a little more complicated, just like frequency encoding matrix was. So this week we're going to dive into K-space and the relationship between the phase encoding gradient and K-space. And also the frequency. It's just the frequency encoding gradient. We understood most of that last time. It doesn't have as much to do with K-space like the phase encoding gradient does. So in the same way that the last couple of lectures, we've kind of dealt, the first half of the lecture is going through some physics. And then the second half has been talking about some of the aspect of scanning, right? 2 weeks ago, we did encoding 2, and then we talked about resolution. Last week in encoding 3, we talked about SNR. This week, we talk about time. Right? So after we're done talking about K-space, we're going to talk about acquisition time in MRI. And the reason for that is because the acquisition time of a sequence is simply how long does it take to fill up K-space with echoes. Right? Once we've filled up K-space with echoes, we're done scanning. So that's why K-space and time go hand in hand with each other in a lecture. Because once we've finished job of filling K-space, scan's over. That's what determines your scan time, how long it takes for you to fill up K-space. All right. So we'll talk about the time. And the other difficult thing is that we are going to get into some math this week. Now, 2 weeks ago in encoding 2, we talked about mathematically figuring out the size of a pixel. Frequency field of view divided by frequency matrix times phase field of view divided by phase matrix. This week, we're going to introduce the time equation, and you will have to do math. You will have to take the different parameters out of a pulse sequence. You will have to do the math to calculate how long it would take for that scan to run. The hard part about that is then converting milliseconds into minutes and seconds. You have to do some conversion after you get to your answer in order to come up with the correct answer. There will be math questions on the quiz. There's also a practice test that I will make available after the lecture. It has some time equation questions, so you can work on them on your own time, and you'll see the answer when you're done with them. It's not for points, but if you want to go in and have some practice doing this time equation, because it can get a little complicated, that'll be available as well. And you can definitely expect to see that on the final exam. On top of that, in physics 2, we introduce a different time equation for a fast spin echo, a different time equation for a gradient echo, and then a different time equation for 3D imaging. So all of those are variations on the time equation we learned this week. It'll be very hard to do the time equations for fast spin echo and gradient echo in 3D if you can't do the baseline equation, because all those equations are a change to this baseline. So there's a lot of very foundational information today, things that are going to be used and carried over into Physics 2. Things you say today will be answered on the Physics 2 final, because this is all cumulative, right? So pretty important lecture. But like I said, I don't think conceptually it's harder to understand or as hard to understand as last week's sampling lecture, because that one's a beast. Okay. Well, let's get into the lecture. All right, K-space 1, physics 1. So the ART objectives we're going to talk about today. We're going to talk about phase and frequency. We're going to talk about K-space, which is the raw data of an image. We're going to talk about NSA, or number of signal averages. They're called NSA, NEX. I think Hitachi calls them number. And I know they're also just called averages by a lot of people. They're all the same thing. We're going to stick with NSA because that's what the ART likes. So we're going to stick with the term NSA. But like I said, depending on what machine you're on, there's lots of different names for this. And then acquisition time, how long it takes to acquire our images. Now, they use the term acquisition time here because in MRI, time could mean different things. We could be talking about the time between heartbeats. We could be talking about the amount of time it takes for a patient to hold their breath. Right? So acquisition time specifically means how long does it take to run your pulse sequence. All right. Okay, K-space. Mystical, magical, crazy K-space. All K-space is an area in which we store data before we turn it into an image. I think of it as an empty bucket, right? And all we're doing is we're going through our scan and collecting echoes, and every time we get an echo, we throw it in the bucket, and when the bucket is full, We can turn that into an image by dumping all the echoes out. So it's just a storage area. In reality, K-space doesn't exist as a physical anything. It's calculations done by a computer. Right? K-space does not, there's no physical place where K-space is. It is just a way to explain how the computer is gathering and then processing the data points that we pulled out of the signal, right? Last week we sampled. We took data points out of the echo. Well, we put those data points into K-space, and then through a process we'll talk about today called the fast Fourier transform, we turn that data into pictures. We care about this because next week we're going to talk about all the ways that we can manipulate K-space to make our images go faster or look better, right? Zip 512, acquired versus reconstructed matrix, those are ways to manipulate K-space to improve resolution. Parallel imaging, half Fourier imaging, those are ways to save time by manipulating K-space. All right. So we have a bunch of different techniques as technologists we use to manipulate how we put data into K-space to do things like improve resolution, change contrast, or decrease scan time, right? All of these things that we like to do, increase SNR, right? That's what we like to do in MRI, right? We love to have short scans with great resolution, high SNR, and perfect contrast. So understanding how we can manipulate K-space to help us get there is the reason why we learn about K-space. All right. So K-space, data of each signal position are collected. The information is stored as data points in the array processor of the system computer. So the array processor is a physical part of the computer, right? Where we store the information. That's where K-space is happening. Right. Each slice has its own K-space. If I'm making 15 slices, then I have 15 different K-spaces. There is one K-space per image. How many K-spaces? That depends on you as a tech. You enter in the number of slices you want for a sequence. Then the computer says, okay, you want 17 slices? Then I'm going to create 17 K-spaces, one for each slice. So every slice has its own K-space. So if you run a poll sequence with 15 slices, you will have 15 K-spaces. Looks like it says 15,000 there. Got 15 K-spaces, right? So to understand K-space, we use a lot of different models of what we think are ways to understand it, all right? But like I said, in reality, K-space is numbers in a computer. This is one way we can think of looking at K-space, and this is another. If you were to go into the computer and say, instead of giving me an image, just give me a printout of what K-space looks like, the computer will give you this. This is an actual MRI image. If you were to take this image and put it through the fast Fourier transform, it would give you an MRI image. All right? And the fast Fourier transform is just a bunch of math. It's just a very long algorithm that turns this information here into black and white pixels on the screen, right? In shades of gray, all the different pixels on the screen. So these are the two models that we like to look at for K-space. For our purposes, because it explains everything better, we're going to be talking about this one because it helps us understand how to manipulate K-space and what's going on. Because here we're looking at a bunch of echoes that we've collected. Right. Now, like I said, these are both just models for trying to understand what K-space looks like. In reality, you don't ever look at K-space. So it's just a bunch of models. So K-space has two axes, frequency and phase. This correlates with the gradients used with the patient. As we've been talking about this is week number 4 now, we're talking about gradients, phase encoding and frequency encoding. Right. K-space holds data points until it's time to convert the data into an image. Another way you could do another model of K-space would be this. In here, we're showing the echoes that we're collecting, but here we're showing those echoes turned into data points, right? So here's the echo, but in reality, the frequency encoding gradient has sampled it and turned it into echoes, or turned it into data points. Taken this echo while it's being generated in the patient and turn it into data points in K-space. So this model of K-space is showing us the same thing, except here we're just seeing the data points that we're taking out, right? Here, if we were to count the frequency matrix, it would be 1, 2, 3, 4, 5, 6, 7, 8. That's just many, 16. So we'd have a frequency matrix of 16 because we have 16 data points. All right. So one more thing before we get farther into the. So we talked a lot about how we have the patient inside the machine. And over here, we have our image. Over here, we have a phase encoding gradient, and we have a frequency encoding gradient. And on the image, we have a phase matrix, and we have a frequency matrix. Between the patient and the image is where we have K-space. And here we have a phase axis and a frequency axis. So just like before, we have a phase direction, a phase axis, and a phase matrix. The phase encoding gradient exists in the machine. The phase axis is in K-space, and the phase matrix is on the image. Same thing with frequency. We have the frequency gradient in the machine of the patient, a frequency axis of K-space, and then a frequency matrix of the image. So we have patient to K-space to image. From the patient to K-space is where sampling is happening, what we talked about last week. And from K-space to the image is the fast Fourier transform, which we'll talk about this week. Just to kind of give you an idea, when we're talking about K-space, we're talking about a place that we're storing these echoes as we collect them out of the patient. We take an echo, we put it in K-space, then another echo, put it in K-space. Once K-space has all of its echoes filled up, then we'll do the fast Fourier, then your image appears on your screen. Once again, the total amount of time to do sampling, to fill up K-space, to do the fast Fourier, that will be the time for your pulse sequence. The speed, the time at which that happens. All right. So K-space has two axes, frequency and phase. This correlates with the gradients used in the patient. K-space holds data points until it is time to convert the data into an image. Each row of K-space stores an echo. So every row of K-space is going to store one echo, which is why we like this model of K-space, because it shows us that. So each one of these teal lines here is one echo that was collected out of the patient. Right? So the first time we did a 90-degree excitation pulse, we filled up a line of K-space, and then we kept going till we filled up all of K-space, and then the image is done. Let's take a look at my favorite thing in the world, animations. So here is a picture. We're looking at just K space and then the image, right? The patient is not shown here. So as we fill up K space, we start to create the image. So we fill up one line of K space, then the next line of K space. Every one of these lines of K space is a different echo. There's an echo, there's an echo, there's an echo, right? And each one of these echoes had a 90-degree excitation pulse, a 180. We collected the echo. We waited till time TR and did another 90-degree, and so on and so forth. So we just keep going. And as we go, we keep filling up more and more of K space until we fill up all of K space. And once we filled up the last line of K space, the slice is done. Then we can go on to the next K space, right? And fill it up until we fill up all the slices we need. So this picture here, this table here, is just showing all the different echoes that we collected for this particular scan. All right. We're going to talk about why that's important in a little bit, but that's what it's showing us. We know that this is the phase axis because each line of K space here, or each what we're going to call a row, we have to use the terms row and column because that's what the ART likes, even if I don't like that term. It's kind of confusing. But this is a row of K space. There are also columns of K space, which we'll talk about in a minute. So this is the phase axis. Each one of these echoes we have talked about needs to have a unique amount of phase encoding, a unique strength of the phase encoding gradient. Right. The frequency is from left to right because the frequency encoding gradient is turned on while the echo is being collected. So here's the frequency encoding gradient creating the data points to fill up K space as we go. When we label K space, we are going to have a positive and negative side of K space. But we're all going to have two positive sides of K space and two negative sides of K space. The reason for this is if we think about the gradients. If we look at the frequency encoding gradient, each one of these echoes was collected with the same strength of the frequency encoding gradient, right? Damn my horrible drawing skills. All right, let's try that one more time. Positive side of the gradient and a negative side of the gradient. So each one of these echoes, we can imagine that I drew the line correctly, and this was isocenter. This side of K space was collected with a negative power of the frequency encoding gradient. And this part of K space was gathered with a positive side of the frequency encoding gradient. So all of these echoes, the part of these echoes are all positive for the frequency encoding, and all of these are negative. In the same way, down here we have our phase encoding gradient. Here we have the positive part of K space and the negative, according to the phase encoding gradient. So all of the echoes collected up here, up top, are all collected with a positive lobe of the phase encoding gradient, and all those below are called with the negative. All right. Remember, we talked about polarity. We're going to use the word polarity a lot today. Poles, positive or negative, right? So the polarity of the protons here are positive in the phase direction if they're in the middle, above the middle of K space, and they're in the negative polarity if they're bottom half. For the frequency encoding, they're in the negative polarity if they're on the left-hand side of K space, and they're the positive if they're on the right-hand side. So when we say positive side of K space and negative side of K space, we are referring to the polarity of the frequency or phase encoding gradient. So when we label our echoes in K space, positive 128 and negative 128 are the same echo. Just one was made with the positive side of the phase encoding gradient and one was made with a negative. But when we look at the gradient being right at isocenter, best as I can draw it, right? That means this gradient had just as much power in the positive direction as this gradient had in the negative. So when we label K-space, we label the echoes in the center closest to isocenter as +1 and -1. Then we go this way in the positive direction, so we have echo 1, 2, 3, 4, so on and so forth. This K-space has 128 positive echoes and 128 negative echoes. That means the total amount of echoes it has is 256, because 128 plus 128 is 256. This would be a pole sequence run with a phase matrix of 256. If I run a pole sequence with a phase matrix of 256, I have 128 echoes made with the positive lobe of the phase encoding gradient and 128 made with the negative. Positive and negative doesn't mean the echo is any stronger or any better. It is a directional thing. Is it in the positive side of the gradient or the negative side of the gradient? Negative 128 doesn't mean we're taking away anything, and it doesn't mean it's a weaker echo. It just means it was in the negative portion of the gradient when it was created. Right? So lines of K-space are usually numbered with the lowest number near the central axis and the highest number towards the outer edges, right? We have 1, 2, 3 in the center, and then negative 128, positive 128, 126 towards the outside. The top half of K-space are called positive lines, and those in the bottom are negative, right? So we know that the phase encoding gradient has to change its strength with every echo we collect. Because when it comes down to looking at this, the way the computer knows where each one of these echoes should go in K-space is based on what the echo looks like. This echo has a certain shape, so it's placed here in K-space, and so on and so forth. Every echo must be unique. No two echoes can be the same. If they are, you have an artifact called motion. When you have echoes that look the exact same, but they're in the wrong place in K-space, that is what motion artifact is. When a patient moves and their anatomy is no longer in the same spot, then the phase encoding gradient ends up putting the wrong information in K-space. The technical name for motion artifact is phase mismapping, because the computer put the wrong echo into the wrong spot in K-space. It thought it was the right spot, and it was the right spot until the patient moved. Now the patient's anatomy is in a different area. So what does the computer do? It compensates for this by putting that information across all of K-space. So determining where information goes into K-space is the job of the phase encoding gradient. The phase encoding gradient determines whether information goes in the top half of K-space, the middle of K-space, or the bottom half of K-space. Every single echo has to have a different slope of the phase encoding gradient. The phase encoding gradient changes its strength every time we collect a new echo. The frequency encoding is always the same. We don't change the strength of the frequency encoding. Every single echo is collected with the same amount of frequency encoding, so we have the same number of data points. So once again, coming back here, watching us fill up K-space. Look at the phase encoding gradient and look at the frequency encoding gradient. Every time we finish filling one line of K-space, the phase encoding gradient will change its strength. It's starting here in the positive end of the phase encoding. Collect another echo, look at changes, and then it's getting a little bit weaker and a little bit weaker because we're going towards the center of K-space, right? We get to the middle of K-space and the gradient is basically completely turned off. But now we need to fill the negative end of K-space. So the phase encoding gradient continues to change with every single echo going into the negative direction. So the phase encoding gradient is changing its strength every time we collect a new echo to fill up a different line of K-space, right? So as the phase encoding gradient changes, the echoes themselves are being altered and they're becoming different so that we can fill up different lines of K space. Because once again, if we fill up the same line of K space twice with different echoes, right, then we get motion artifact. Right? That's exactly what motion artifact is. It's a mismapping of K space information. The computer did what it was supposed to, but the patient moved where their anatomy was, so echoes went in the wrong place in K space. And then when the fast Fourier transform turned that into an image, it had all this extra information, and so it just basically spits it out over your image going in the phase direction. Okay, so each line to be filled with data in a given TR is determined by the polarity and slope of the phase encoding gradient, right? Because the polarity tells us whether we're in the top half of K space or the bottom half, positive and negative, right? If we look at these echoes, if we look at the two middlemost echoes, we can see that these echoes are the exact same. They have the same height and peak of their echoes here. And then we can see the echo in positive 2 is the same as the echo in negative 2. Just in the way the very last echo at positive 128 has the exact same shape as the echo at negative 128. So every time we go to collect an echo, each echo has a mirror image of itself in the positive and negative directions. We just know where they go because we knew the gradient was positive or negative. Right. So each line has to be filled. Oh, we said that. So polarity and slope of the phase encoding gradient. All right. If the phase encoding gradient is not changed, then the same line is filled every TR. The total number of lines in K space is equal to the phase matrix. So let's talk about this. So here we have these different echoes. Amplitude here in the talking about in the echo, we're talking about how much signal amplitude there is in the echo. Every echo contains the same amount of noise, right? They all contain the same amount of noise. But as the phase encoding gradient gets stronger, the signal gets lower. Once again, you can see the peaks are very high here and very low here and here. We open one thing up real quick. Just gonna grab an image from last week's lecture to drive this point home. So all of these echoes have the same amount of baseline noise. The higher the peak, the more signal they have. So as the peaks get smaller, they have the same amount of noise, but the amount of signal becomes less. So these protons have lower SNR, and these protons have higher SNR. Because SNR is the signal to noise ratio. Not the total amount of noise, not the total amount of signal, but how much signal versus how much noise. If I have echoes that have more signal or less signal. So why does this matter? Or why does it look this way? So what the phase encoding gradient is doing, it is dephasing protons. If we have the phase encoding gradient, and it is basically turned off, barely turned on at all. Then that means all of the protons that are spinning when we go to collect the echo, they are mostly going to be in phase. Which means that we can add all those protons up together and get a very strong net magnetic vector when we go to make the echo. If you have on a phase encoding gradient with a very steep slope, it will dephase the protons more, right? It will make the protons much more dephased. And now these protons are not all pointing in the same direction. So their magnetic power is a lot less. Net magnetic vector. But the amount of noise between these two is the same. They have the same noise. But over here, we have a stronger net magnetic vector, and over here, we have a weaker one. So when we go to make the echo, these protons are mainly in phase. So what do? They create an echo with really high peaks. Where over here, there's a very weak magnetic vector, so their peaks are going to be much smaller. Now, how many total peaks they have is what we talked about last week. But the height of each peak, right, that's determined by the amount of signal. The amount of noise is the same. But if we add up all of the signal underneath here, compared to how much signal we have over here, we don't have very much. This echo generated with a very weak phase encoding gradient generated an echo which had a higher SNR value. Where down here we had less signal and the same amount of noise, so we have a lower SNR value. So when we go to scan, as we increase, now we have to have a different amount of phase for every single echo. You can't collect them the same, or they don't know where they go in K-space. All right? So a shallow phase encoding gradient leads to more SNR. And a steep phase encoding gradient leads to less SNR. All right? So, steeper the phase encoding gradient, the lower the SNR. Yes. Yes. This is directly related to the phase matrix, which we're going to talk about next. Yes. Because the phase matrix is how many total echoes you're collecting to fill up K-space. That's what the phase matrix is. And no two echoes have to be exactly the same. Right? So if I have a low phase encoding gradient, I will use shallower, or if I have a low phase matrix, I will use shallower phase encoding slopes and have more SNR. But if I use a stronger phase encoding gradient, I will have steeper slopes and less SNR. All right? I'm going to get more into that here, Omar, but there's a couple pictures I want to show. Okay. So, steep gradient leads to low amplitude signal. Low amplitude means you can just take the word amplitude out of this. Low signal. They all have the same noise. So this has a decreased SNR. Where those in the middle have an increased SNR. High signal for a shallow gradient. All right. So yes, the total number of lines in K-space is equal to the phase matrix. So you get to choose how many lines of K-space are needed, or how many lines are needed to fill up K-space, how many rows there are. That's what happens when you choose the phase matrix. You are telling the machine, hey, okay, I want to run the scan. My phase matrix is 256. The computer goes, cool. That means you need 256 echoes for every K space. And then you hit go, and then the machine does that. It repeats until it fills up K space. All right. And if it doesn't fill up K space, you don't get an image. Some of you may have seen this before, where you're scanning like a 3 or 4 minute scan, and then the patient squeezes the ball, and you hit the stop button, and you had 10 seconds left on the scan, and then you get no images because you filled up most of the K spaces. If your K space, if you say it needs 256 and you fill it up to 255, and then you hit fast Fourier transform, the computer says, no, you get nothing. Everything is trash. Throw it all away. It must be filled up with the amount of K space. Now, there's acquisitions and other things like that that we'll talk about later about why you sometimes see some of those images. But no image will be formed unless you fill up all the lines of K space. I want to come back to this. No. Oh, no. Okay. So once again, we change the phase encoding gradient every TR. Right. In this picture, we're changing the amplitude of the echo based off of TR1, that was our phase, TR2, that was our phase, and then we change the phase with every TR. Right. And in fact, one of the problems that we have, wrap, happens when the echoes down here appear the same as this one, and then they both go in the same spot. Because once again, wrap is just another problem of putting information into K space, right? So the phase shift is what creates different lines of K space, right? What we mean by phase shift is we're talking about the strength of the phase encoding gradient shifting the phase of the protons, right? Each TR has a different phase value, which is created with a different strength of the phase encoding gradient. Steep phase gradients, both positive and negative, select the most outer lines, while shallow gradients select the central lines. We are going to use this a lot when we get into physics 2 and we talk about fast spin echo. Because in fast spin echo, we have to manipulate where echoes go in order to preserve the contrast of our scan. So we're going to use shallow gradients in the middle of K space and then steep gradients on the outside of K space. As the slope of the phase gradient decreases from its steepest slope, the lines through K space are stepped down from the most outer lines to the most central lines. So once again, as we watch here, the phase encoding gradient starts off very strong in the positive direction, and then slowly is creating stronger and stronger echoes because the gradient is getting shallower until we get to the central of K space when the gradient is almost turned off. So these are very, very high signal echoes. And then as we go into the negative direction, the gradient becomes steeper and steeper, meaning each progressive echo has lower and lower SNR. The phase encoding gradient changes every time we collect an echo. It has to, right? It has to. Otherwise, we would put information in the same spot in K space, and we would have motion artifact without a patient moving. As that phase encoding gradient, the strong part of the phase encoding gradient happens on the outside of K space, and towards the middle of K space, we have a very shallow phase encoding gradient, right? And shallow phase encoding gradient give us echoes with more signal. So we need to change the amplitude of the phase encoding gradient to fill different lines of K space and therefore create multiple pixels in the phase direction of the image, right? Because each different application of the phase encoding gradient creates a different pixel in the phase direction. Because remember, our phase matrix also tells us the number of pixels on the screen. Inside the patient, it's the number of different application of phase encoding to generate that many different echoes. In K space, it's the number of rows of K space we create. On your computer screen, the phase matrix is the number of pixels in the phase encoding direction. So once again, When you're talking about the phase matrix and what it's doing something in the patient, it's doing something in K-space, and it's doing something on the screen. In the patient, it's using different strengths of a gradient. In K-space, it's telling us how many rows we need to fill up. And then on the screen, it's how many pixels are in the phase direction, right? So phase matrix controls all three of those things. Just like frequency controls the strength of the frequency encoding and field of view in the patient, where information goes in the frequency axis of the K-space, which we're going to get into a little bit later, and then the number of pixels in the frequency encoding direction on the image. Altering the frequency encoding gradient would change the pixel size in the frequency direction. Thus, it cannot be changed every TR. The frequency encoding gradient strength stays the same throughout every single echo you collect, based on receiver bandwidth, frequency field of view, and frequency matrix, which is what we talked about last week. The slice select gradient determines slice thickness, so it doesn't get changed every TR because it has to turn on to determine where we're causing excitation to occur to determine what the slice is. So the slice select gradient always stays the same as well. Altering the so only the phase encoding gradient changes strength every TR. One more thing. That is why when we're using this picture of our pulse sequence diagram, this is why we use this symbol for the phase encoding gradient, because it's showing that for one echo, it'll turn on positive in the positive direction, and it'll turn on in this, and it's showing that every single time you collect an echo, you're changing the strength of the phase encoding gradient. That's why we use that symbol. Whereas slice select, it's just showing one strength of the slice select gradient and only one strength of the frequency encoding gradient. But we use this symbol with the phase encoding gradient to show that the strength of the phase encoding gradient changes with every echo, right? Remember, this little box here is showing us that the gradient's turning on in the positive direction to a certain strength and the negative. The phase encoding is showing us there's a whole bunch of different positive it turns into, and there's an equal amount of negative it turns into. It has to change for every echo we collect. That's why we use that symbol for phase encoding on the pulse sequence diagram. Oh, there's it right there. Next one. Okay, so each gradient determines where data points from an echo are stored in K-space. Right. The slice select chooses which K-space will receive the echo. Right. Phase encoding determines which line of K-space will be filled, and the frequency determines where the data points are stored left to right. Let's take a look at that real quick. So MRI in practice, the authors like to use this analogy of filling socks into a chest of drawers. So here we have the slice select gradient being turned on first. Here we have, here's a pulse sequence diagram, and then we have three chests of drawers. This is representing an image or a pulse sequence with three slices. Right. So we have three different case spaces. All right. Slice select. It's going to choose which chest of drawers, which case space, phase encoding, which drawer, and then frequency encoding turns on when the data points are happening. So first off, slice select gradient turns on and chooses the first drawer. Now, once again, notice how we have all these different strengths of the phase encoding gradient. In fact, there's 1, 2, 3, 4, 5, 6, 7, 8 different strengths it will turn on. Why? Because there's 1, 2, 3, 4, 5, 6, 7, 8 rows of K space. And every row of K space needs to have a different strength. So the phase encoding gradient turns on to strength uh, positive 3. It goes down, and the phase encoding says, okay, that's the strength of the phase encoding gradient. That means the third row of K space needs to be filled. Then we do the 180. As the echo is formed, now the frequency encoding will turn on and collect the data points. So from left to right, it determines where the data points go while the echo is being generated. So slice select tells us which K space we're in. Phase encoding tells us which row of K space. And then frequency turns on and samples and gets data points and stores those from left to right in K space. After that, we can go to the next chest of drawers. Slice select tells us we're in drawer number 2 now. Now, drawer number 2, the third drawer hasn't been filled up yet. So the phase encoding turns on number 3 for slice 2 and then fills up K space. Data points left to right. So for this phase encoding gradient, there's one strength for all of K space, right? There's one strength for every row in K space. But each of these is going to be applied to each K space because I have to fill up drawer 1, 2, 3, 4, 5, 6, 7, 8 in slice 1. Then I've got to fill up drawers 1, 2, 3, 4, 5, 6, 7, 8 in slice 2, and so on and so forth. So this is how our 3 spatial gradients, we've already talked about in encoding, how they turn on and change the protons in the body. This is how, when we go to actually collect the data points, how the computer knows where those data points came from. This is where we are decoding, right? We were encoding all that information with these gradients, and now we're sticking it all into K space. We know where it goes in K space based off of how strong the gradient was while we were running it. What are our questions? All right, I'm going to open up the webinar questions, and I'll see y'all at the top of the hour. All right. Okay, we are back. Let's look at questions here. Okay, the number of lines of K-space collected is dependent on the phase matrix. It's the number of lines collected. The phase encoding gradient must create a phase shift once per TR, because every TR we collect an echo, right? So we have to have a phase shift every TR. Steep of the phase encoding gradient determines the line of K-space to be filled, right? Number of data points is frequency matrix. That's the slice select. This is TR and T. There's one K-space for each slice. Every slice has its own K-space. And K-space has two axes, frequency and phase. Yes, that is true. Okay. So let's talk about inside and the outside of K-space. So where data is stored in K-space determines how the final image is created. It determines where this particular data points are used for different things based on where that information is stored in K-space. Whether it's towards the center or towards the outside of K-space is going to change how that data is used for the final exam. All right. So we break K-space up into two areas, the center and the outside of K-space. Understanding how we take advantage of these is going to explain how we collect information for contrast enhanced MRAs. It's going to change how we collect information for fast spin echoes and so on and so forth. So understanding this difference is once again key to understanding how we take advantage of this difference when we're making different types of images. So once we, again, the steepness of the phase encoding gradient determines how strong an echo is when it is created. Is it a high signal or low signal? Steep slope and phasing gradient leads to dephased protons when the echo is created, leading to low amplitude signal. So low SNR, right? Low signal, same amount of noise, low SNR. All echoes have a constant amount of noise, so the lower the signal amplitude, the lower the SNR. When we fill K-space, we will put the signals with the highest SNR into the middle of K-space. Right? The highest SNR will go into the middle of K-space. So if we look at our different applications of the phase encoding gradient here, as the phase encoding gradient becomes more steep, we can see these echoes have lower peaks, which means they have less SNR. When we get down here where we don't have the gradient turned on at all, we have very strong peaks. So those echoes we want to put towards the center of K-space. Where the echoes out here that are very weak, we are going to put towards the outside of K-space. Right? So as we go and we run our pole sequence, we are changing the steepness of the phase encoding gradient with every echo. Every echo looks unique. Every echo goes a different place in K-space. Strong echoes towards the center, weaker echoes towards the outside. All right. So let's take a look at some animations. So what this means is that we can expect the strongest information to go into the middle of K-space. Now we are going to use, when we make an image, we are going to use the center of K-space to give us both SNR and the contrast of the image. Let's take a look what that looks like. So here we have an image and here we have K-space. This image has both resolution and contrast and SNR to it, right? Time is no longer matter because at this point we've collected all the echoes. So time is over. So time doesn't matter here, right? We're past the point of time. The same thing with slice select. Slice select doesn't matter anymore because we've collected all the echoes. But the contrast, SNR, and resolution for the image is based on how we do K-space. So when we say So when we say the center of K-space gives us contrast in SNR, this is what we mean. In this video here, what we're going to see is we're going to see what happens when we take away the outside of K-space, and we're left with only the center information. As we take away the outside of K-space in the image, we start to lose the resolution or the sharp lines. This is a picture of an image that has contrast and SNR, but has zero resolution. Contrast, we have areas of gray, right? We have some areas of black, some areas of white, and lots of different shades of gray. Because the middle, very middle of K-space gives us all of our contrast in an MRI image, all right? On the other hand, we take away the center of K-space and we remove the contrast and SNR, all we are left with is resolution, sharp lines. So the outside of K-space is giving us the resolution of the image. Right? As we remove more and more of the center, we are left with less and less SNR. So we are left with, once we get to the very outside of K-space, we have nothing at all. Once again, watch the image as it forms. We're filling up the outside lines of K-space. And as we do that, we start to form resolution, right? Because we're getting those outside lines of K-space. Now we can see the lines, the outline of the brain. And as we start to fill up the middle, we suddenly start to get contrast and signal. But the image still looks kind of blurry because we're going to fill up the outside lines on the bottom half here, adding more and more resolution, making the image sharper and sharper till we have our final image. So as we collect echoes for our image, those that are collected at the top and bottom half of K-space, the outside of K-space, those make up the resolution of the image. But those echoes in the center of K-space give us our contrast. What's the different shades of gray so we can actually see what's going on there. Other thing to notice here is look at the strength of the phase encoding gradient. When the phase encoding gradient is strong in both the positive and negative direction, we're creating echoes that give us resolution. As that gradient becomes shallower, we end up with more signal and less noise in the echo. Those echoes with large signal compared to the noise give us contrast and resolution. So the gradient, and now we go back to resolution as we go, right? So the outside is resolution, the inside is SNR and contrast. So steep phase encoding gradient, right, creates low SNR echoes that we put into the outside of K-space. Shallow phase encoding gradient applications give us echoes with strong SNR, so we put them in the middle of K-space. When the computer turns K-space into an image, it's going to read the data in the center of K-space and turn it in and use it for the contrast and SNR for the image. So when we have this information, you can see in this drawing of K-space that we have bright signal towards the middle. These are the highest points of SNR, were those created at the middle of K-space. We're out here, these data points are very dark. Those are used to make the resolution of K-space. Right? Choosing which echoes go in the middle allows us to do lots of different things in MRI. It's what makes fast spin echoes possible. Okay. So when it comes to resolution, the amplitude of the signal does not matter. All right. It does not matter. When I go to make those outside lines of K-space, it doesn't matter if my echoes have a lot of signal in them or not. All right. So when we choose which echoes we're going to use for resolution, that's why we're choosing echoes with very low signal amplitude. Because the SNR for the image is going to be determined by the center of K-space. Also somewhat the outside of K-space, just not as much. All right. This means all signals, regardless of amplitude, whether they're high SNR or low SNR, have the same value when it comes to resolution. When it comes to resolution, it doesn't matter if I have a high amplitude or low amplitude signal. For this reason, we use low amplitude signals in the outside of K-space to create resolution. All right. So the central portion of K-space contains data that have high signal amplitude and low resolution. The outer portion of K-space contains data that have low signal amplitude and high resolution. Right. So, coming all the way back to what you were talking about, Omar. We're coming back to the phase matrix and the different amount. So, if I'm going to go and create an image, here we have two different K-spaces. One being represented by a phase matrix of 256, right? So we're going from positive 128 to negative 128. And then over here, we have 128 phase encoding, 64 and negative 64. So knowing that all of the echoes are just as good for resolution, when we choose a matrix like this one at the bottom of 128, we are going to make the strongest echoes possible by using the shallowest applications of phase encoding gradient we can. But as I increase that matrix, that phase matrix, I'm going to fill up more and more the outside of K-space. Right. So as you increase your phase matrix, you're generating more echoes, but those echoes are weaker and weaker. Because in order to create more and more echoes, we're going to use steeper and steeper phase encoding gradient applications. Coming back here I have 1, 2, 3, 4, 5, 6, 7 echoes being generated. Well, let's say I only needed 3 echoes. Well, which echoes would I generate? Those with low signal or those with high? I would choose to only make these 3 echoes with the shallowest phase encoding gradient because they have the most SNR. So whenever we're setting our phase matrix, we are going to be using the shallowest gradients we can to create the signals with the highest amount of signal to noise ratio. I'm not going to create weaker and weaker echoes unless I need more resolution, because the outside lines of K-space give me resolution. So when we choose a phase matrix, if I choose a low phase matrix, then I'm going to make echoes that have more SNR, and I'm going to put them in the center of K-space, and I'm going to have an image with a high SNR. However, I didn't fill up much of the outside of K-space, did I? Which means I will have lower resolution. However, up here with my higher, now I have more echoes, but look how weak they are. This one's basically a flat line, not much signal. So when I average all of these echoes together to create my image, I will have less SNR because I had to use steeper and steeper applications to fill up that outside of K-space. But because I filled up more of the outside of K-space, I have more resolution. So given a choice, we are always going to make the echoes and put them in the center of K-space first. We aren't going to use stronger and stronger phase encoding gradients unless we need to get that resolution. But as we do that, we create weaker and weaker echoes, which means the total SNR for our scan is going to decrease. All right. This is what's happening when you're changing your phase matrix. When you're changing your phase matrix, this is what's happening. You're adding more and more echoes. When I take my phase matrix up, I add more echoes to the outside of K-space, which is going to increase my resolution because the outside of K-space is what I use for resolution. But I'm making weaker echoes. So my total SNR is going to go down. because every single echo is going to bring me the same amount of noise, but every new echo I have to generate is going to slowly give me less and less and less signal because I have to use a steeper and steeper phase encoding gradient to generate a different echo. All right. So yes, as you get a high phase matrix, to answer your question, Omar, so to get to a high phase matrix, yes, this is relative to the phase matrix. The more echoes I create, the steeper my phase encoding gradient has to be, decreasing SNR, increasing resolution, because I'm filling up more of the outside of K space. Right, so that's what this picture is showing you here. As I increase phase matrix, I create more and more echoes on the outside of K space. So we choose a phase matrix, the machine will create the central lines of K space first, followed by the outer lines. Right? If I had a phase matrix of 2, I would fill up line 1 and line -1. If I went to a phase matrix of 4, I would fill up line +1, +2, -1, -2. If I had 6 lines, 6 phase matrix, I would fill up lines +1, +2, +3, -1, -2, -3. So I would start in the center and build my way out, because as I build more towards the outside, I'm losing signal. And every single echo is the same for resolution. As we add more lines to K space, by increasing our phase matrix, we add more low amplitude signals to the outside of K space. This is why resolution increases as we increase the phase matrix. So phase matrix goes up, which is also the number of pixels on the screen. So as I go from 128 to 256, I now have more echoes to give me more data points, to give me more pixels in the phase encoding direction of the phase matrix, the phase direction of the image. We're going to get to data points in just a second. So, but the SNR of the final image is the average of all the signals in K space. As you add more and more low amplitude signals, the total amount of signal in K space decreases while noise remains constant. Increasing the phase matrix leads to more noise, as each new signal has a constant noise value, but less signal, as each new signal has a lower amplitude. Thus, increasing the phase matrix decreases SNR. So in this example, we have a matrix of 256 by 256. As we start taking that phase matrix down to 192, 128, 64, the resolution drops more and more and more and more. Right? Because we are simply filling out the less and less of the outside of K space. It should also have more. This one, if you look at it, I don't know how well it's coming across your screen. If you look at it on the lecture and blow it up pretty big, this one is grainy. Right? This one is kind of grainy. I don't know if that's coming across when I'm sharing. Sometimes the Google Meet, the images don't look that great. But this one is grainy. As that matrix gets lower over here, now our resolution is very poor, but there's no more of the graininess. So as we decrease the phase matrix, our resolution got worse, but our SNR got better. Because here we're only collecting 64 echoes and putting them all in the middle of K space. Here, we're now doubling it, collecting twice as many echoes, which means that we collect the same 64 echoes, but we collect 64 weaker echoes as well, because we had to use stronger, steeper phase encoding to make lower amplitude echoes. And then here, once again, we increase it and increase it again. So phase matrix goes down, it decreases SNR. I'm sorry, as the phase matrix goes up, it decreases SNR, because we're generating weaker and weaker echoes. Okay. Why do the proportions of the images look the same even though the pixel size? What do you mean by the proportions of the image? Oh, that's because the field of view remained constant. The field of view remains constant. So the pixels got bigger, which is why it looks less. And if you say, like, let's see how far I can zoom in on this. They aren't necessarily saying proportional. Take a look at the slip disc. Take a look at the bulging disc right here, and take a look of it here. Those are not proportional. Those are actually differently shaped. This one is bulging out like a big circle, and this one is coming in like a sleep one like that. So if you take a minute and really zoom in and look at it, you're going to see that there is a different shape between these. But the dimensions, the field of view stayed the same. So the information is the same. It's just the pixel got bigger. The pixel got bigger, which means that different amount of information. And this is partial volume averaging. Once again, I don't know how easy it is to see these images through there. But if you look at that bulging disc, there's actually there's a little bit of white right there, showing you a little bit of fluid, which is totally, completely gone here. You can't see that amount of fluid in that bulging disc on that low of a resolution. So yes, there is a change in proportions, but it's not like stretching the image out or anything like that. That's not what pixels do. It's just how sharp and clear the image is, not the shape of the pictures. The only thing that would cause distortion like that would actually make it look distorted, would be gradients that are not working, right? Which is one of the reasons we run the ACR Phantom, because you do those lines to make sure the lines are actually straight. That's testing for geometric accuracy, I think is what it's called, or geometric distortion. So if they were actually had different proportions, that means your gradients there's like a problem inside the machine itself. That's a service engineer issue. So yes, but they stay the same because the field of view is the same. Okay, so K-space is not the image. When I say that K-space is not the image, what we mean is that where information is stored in K-space does not represent where that information is at on the final image. Every echo contributes to every single line of K-space. As we generate it, we push all of the protons down. So what I mean by that is this. If we have a patient, let's say this is their head, right? And then on the final image, we make a sagittal of their head. This information is not stored in the same place as K-space and then on the information. Information in K-space is simply stored as data points. That then gets translated over. So the information of the patient that's here on the image in their nose and here inside of the actual patient, here on the image, that doesn't mean this portion of K-space has that data on it, right? Every echo is created from the entire image, right? So K-space is not the image. If there's information, data on the top half of K-space, that doesn't mean it's in the top half of the patient or on the top half of the image that's generated, right? So data stored in the top line does not end up being on the top of the image, right? So you can't say, oh, something's in the center of K-space. Like, let's say you're planning your slices, right? Here, I'm gonna pull up an MR picture real quick. So here we have a picture of an ankle. Right. The information that was collected in K-space, the information from the patient, when it generated each echo, that echo came from all of the information within the slice because all of that information is excited. Which means that this is not represented. The data from the central of K-space is not the same as the data is not the same as what you see on the picture. K-space is just a repository for numbers. So if I say, oh, well, the middle of K-space gives me the best contrast, so the middle of my image will have the best contrast. No, that's not true. K-space is nothing but numbers, right? You can't center your image better and get a better contrast in the middle. The contrast and SNR is the same throughout the image. It's just that where the information is stored in K-space and then how it gets translated into turning into an image. That doesn't mean when you go set up your slices that something's in the middle of the slice will be in the middle of K-space, which means the middle of your image will look the best. No. It does matter for where you're located when it comes to isocenter for your gradients, but the information that goes into K-space is nothing but numbers. All right. So the middle of K-space doesn't represent the middle of your patient, and it doesn't represent the middle of your image. It is a mathematical domain. It doesn't actually exist. A theoretical construct to explain how we image, if you will. All right. So each data point contains information for the whole slice. That's because all of the protons were all pushed in the transverse plane in the entire slice. As the frequencies that represent it come from the whole echo, and the echo comes from the whole slice. Right? So the middle of K-space does not correspond to the middle of the image. Right? These are two separate things. Okay. All right, so K-space transversal. What we mean by this is how do we determine where information goes into K-space, right? So the RF excitation pulse centers the system into the middle of K-space where the phase and frequency axis of K-space cross. Right? The amplitude of the phase encoding gradient determines how far up and down a line of K-space is filled, right? The steepness of the gradient determines which line of K-space is being filled. The steepest phase gradient slope in the acquisition determines the outermost lines filled both positively and negatively, and in turn determines the size of the pixels in the phase direction of the image. In other words, if I have 256 phase matrix, that determines the number of pixels, 256, and it determines the strongest gradients I will use on the outside of K-space, because I have to use 256 different strengths of the phase encoding gradient. So the polarity of the phase encoding gradient determines whether a line in the top or bottom half of K-space is filled. Positive, top, negative, bottom. Phase encoding gradient is positive, then we are filling the top half of K-space. Phase encoding gradient is negative, fills the bottom half of K-space. Right? So the amplitude of the frequency encoding gradient, among other things, being receiver bandwidth and your frequency field of view, stuff we talked about last week, determines how far to the left and right K-space is transversed, and this in turn determines the size of the pixel in the frequency encoding direction, right? So frequency matrix determines the strength of the frequency encoding gradient, which determines the number of pixels in the frequency encoding direction of the image, right? You gotta remember, there's three things: what's happening in the patient, what's happening in K-space, and what's happening on the final image, right? Phase matrix change all of those things, just like frequency does. Frequency and phase, both. So the frequency encoding gradient is positive, K-space is transverse from left to right. When the frequency encoding gradient is negative, is being transversed from right to left. Oh, I'm actually going to skip that. I'm going to come back to an animation that shows that better. All right. So data in the top half of K-space are identical to those in the bottom half. They are a mirror image of each other. If I was to take and draw a line between the middle of K-space, this information would be a mirror image of this information. Meaning that echo 128 in the positive direction has the exact same shape as the echo at negative 128. It's just one was made in the positive gradient of the phase encoding, one was made in the negative. Echo positive 126 and negative 126 are the exact same shape, just one's positive, one's negative. So they simply have the opposite polarity of the phase encoding gradient, positive or negative. So conjugate symmetry. Conjugate symmetry is the name of what we are saying when we were saying that K-space is the same is a mirror image on the top as it is on the bottom. We're going to talk about next week how we take advantage of conjugate symmetry to reduce minimum TE and do parallel imaging, right? That's what parallel imaging is taking advantage of conjugate symmetry, right? We'll talk about that next week. The same is true for the echo. Every single echo is a mirror image of itself centered on the middle of the echo or the peak of the echo, which is also the middle of the frequency encoding gradient, which is also time TE, because time TE is the time from the excitation pulse to the middle of the echo. So if we take time TE, this half of the echo is a mirror image of this half of the echo, despite my horrible drawing skills, right? These two are mirror images of each other. The left and the right-hand side of K-space are mirror images because every single echo is a mirror image. This represents when the protons are rephasing, then when the protons are in peak, and then when the protons are dephasing again. Let's take a look at the animation for that real quick. Because as the protons rephase, the phase encoding gradient or the frequency encoding gradient has the same strength, so it rephases them just as fast. Then they become in phase, and then they start to dephase as they get onto the negative end of the frequency encoding gradient. So as our protons, you can watch the echo being formed here. They are dephasing at the same speed they rephase. So they're rephasing and generating the echo. And then we get to the peak of the echo. And now we are going to dephase at the exact same speed. So the second half of the echo will be a mirror image of the front half. Now they dephase. We're still reading that. That's part of the echo. So the front half of the echo or the left side of the echo is a mirror image of the right. The echo divided in the middle by time TE is a mirror image of each other. Once again, we will be talking about how we take advantage of that next week to do when we're doing MRAs and abdominal scans. What effect does ARC have? Well, we're going to get really deep into that next week, but basically what ARC does is ARC says, I'm not going to collect the bottom half of K-space. The top half's the same as the bottom half, right? Well, I'll just collect the top half and then have the computer generate what the bottom half should look like. Collecting echoes takes time. So ARC cuts my time down by only collecting half the echoes and then copying the second half. And then we just copy half of echoes. That's what ARC is. That's what parallel imaging is. Right. Like I said, we'll get deeper into that next week. And by doing that, because it takes time to get these echoes, like we're going to talk about here soon, the time, we'll talk about how collecting every echo takes time. So if I collect less echoes, it's less time. So if you put in a phase matrix of 256 and then you turn on ARC, the computer is only going to collect 128 and then create a reconstruction of all of these and make it look like your final image has 256, even though you only collected 128. That's what ARC's doing. All right, why does the number of columns and rows of K-space need to equate to the matrix? Because it is the matrix. That's what the matrix is. If the matrix determines voxels and pixels per echo, why does the amount of echoes also need to be the same number? Well, it's kind of going back like this way. It's how do you, when you tell the machine that you want a matrix of 256 by 128, let's say. So you say, I want 120, or let's say my screen is an MRR image, right? You say, I want 256 pixels this way and 128 this way. This will be my frequency. This will be my phase. The machine says, cool, I can do that for you. But in order for me to figure out, every single one of these pixels has to have different information in it. In order to do that, it inside the patient changes the strength of the phase encoding gradient, the frequency, but it stays the same. And then every echo for 128 echoes gets filled up, right? The K-space is just a way for the computer to translate the signal coming out of the patient into numbers so it can turn it into a picture. Right. So the number of columns in K space equating to the matrix, because that's what it uses to interpolate. That's what it's doing, right? In the same way. For instance, let's say you were a police officer with a radar gun looking for people speeding, right? The people speeding is what you're trying to measure. The radar gun takes the laser and turns that into a number for you. That's basically what K-space is doing. The gun itself is shooting the laser, and then the laser comes back, right, to the gun to see how fast you're going, but it has to translate that data of how fast you're going into numbers so you know miles per hour how fast they're going, right? It's the same kind of idea. It's simply inside the computer. How does it, when you tell it, hey, I want 256 by 128, the computer's like, cool, that means I need to turn on the gradients this strong, but what do I do with that information when I collect it? I got to put it into this matrix so I can turn it into pixels. All right. The matrix determines voxels and pixels per echo because the voxels are generated by the gradients, which turn that information into data into K-space information, data points in K-space. And then we turn the data from K-space into pixels. So it goes voxel, data point in K-space, pixel on your screen. So the matrix is all three of those things combined. It's just how those things are happening. You're telling the computer, hey, I want to see this kind of an image. So it's saying, cool, I need to turn on this many gradients to create these data points in K-space to then turn them into pixels on your screen. So yeah. So yes, the matrix determines voxel size and pixels, right? But like voxels per echo, or voxels or pixels per echo, I don't know if that's exactly the right way to say it. The matrix determines not per echo the total amount, right? So the matrix for the phase encoding determines the total amount of echoes collected, which is pixels in one direction. And the frequency just determines the number of data points taken from the echo. So that's the number of pixels in the frequency direction, if that makes sense. So when you say matrix, it's like two different things. Phase is how many total pixels, how many total echoes we're collecting. And then frequency is how many data points we're collecting per echo. Right. And so ultimately it comes down to this. Right. We take this picture. So in reality, we don't collect the whole echo though, right? We just sample it and create these data points, right? So now these data points, right? We have all of these data points from this echo, right? We sat here and collected a data point, data point, data point, data point. Now with all these data points, we can turn them into pixels. Does that make sense? Clear as mud? Yeah. That is why. Because very simply, it's going to say I have 1, 2, 3, 4, 5, 6, 7. There's 16 rows of 16 rows of information means that it has 16 different pixels that it can change, different colors it can change on the image. That's it. All right. All right. So when we look at our K space, we have the positive side of the phase is up here, and the negative side of the phase is down here. The positive side or the negative side of the frequency is here, and the positive side is here, right? And over here we have positive and negative. So we have these four quadrants of K space based off of the polarity of the phase and the frequency gradient. Not the phase, the polarity. Okay. So that's what we call conjugate symmetry. Right? That is what we call conjugate symmetry. Okay, so what do we do once we have all these data points? What do we do once we have all of these data points? Well, we got to turn them into the picture. And to do that, we use the fast Fourier transform. Right. So an image consists of a matrix of pixels, the number of which is determined by the number of lines in K space in the phase matrix, and the number of data points in each line from the frequency matrix. So every single echo, it can give a different phase, and every single data point, it can give a different frequency. The fast Fourier transform is just a bunch of math. I think of it as a magic black box that you throw all the data points into and out spits an image. As a result of the FFT, each pixel is allocated a color on a grayscale corresponding to the amplitude of specific frequencies coming from the spatial location as represented by that pixel. So if it's a T2 weighted image and that part of the data point has very high signal because it's maybe in the kidney, then it will be bright on the final image. So each row of K-space has the same phase value, but different frequencies values based on the strength of the phase and frequency gradients that were used during the creation of the echo. Each column of K-space has the same frequency value, but a different phase value. You will see that question on the quiz. Make sure you know that phase, each row has the same phase information and each column has the same frequency. I don't particularly like the terms row and column, but the ART does, so that's why we're going to use them. Yeah. So now what we end up with is a bunch of data points, and every data point is unique. Right? Because like we talked about in the resolution chapter, right? They all have either different frequency or different phase information, depending on where they are. Right? So now every data point is unique, and we can turn them into a pixel. All right. Each data point in K-space, therefore, has information from the entire slice locked into it. This information includes spatial frequencies obtained from frequency encoding and frequencies obtained from phase encoding. So this is where the decoding is happening, right? We encoded with the gradient information, and now we're decoding that gradient information through the fast Fourier transform. All right, which once again, it's just math. Bunch of huge, long algorithms. We stick numbers in, and it spits out a color, black, white, or gray. Right? How does it know which color to assign to it? That's based off your TR and TE values because it's contrast. So whether that data point gets turned bright pixel or dark pixel is how much signal there was in the coil when it was generated. How much signal there was in the coil was based off of TR and TE, right? Whether it's a T1 weighted, proton density weighted, or T2 weighted image. So each pixel location has its own unique pattern of frequency encoding and phase encoding, therefore, and there are differing amplitudes of signal at each different pixel location. So here now, we take our data points and we turn them into pixels. Yeah, so in the book, they like to use the term pseudo frequency for phase. I find that confusing, and I've never heard the ART referring to pseudo frequency, so I just kind of gloss over that because pseudo frequency and being the same thing as phase, it's confusing, and I've never seen any ART material with it, so I don't. And if you read the book, which I hope some of you are reading the book is great. You know, the reading assignments are there. They use the term pseudo frequency to refer to phase when it's collecting phase information. I think it's easier to just call it phase because I think then you're like frequency and pseudo frequency. It's on that slide because it's on this picture because I like the picture a lot. But yes, you could change the word pseudo frequency there and just use the term phase. I just find pseudo frequency confusing, so I just don't use it. And I don't think you need to know it for the ART because. So now each data point is assigned either gray or gray, black, or white value, and then generates the pixel. Whether the pixel is white or black or some shade of gray, it's all dependent on TR/TE because that determines which protons were in phase in the transverse plane when you collected the echo, right? It's T1 weighted, then fat was in plane and in phase when you collected the echo. If it's a T2 weighted, then water is in plane and in phase when you collected the echo. Right? Usually when you run poll sequences, I hope everybody's seen this by now, you run an axial T1 weighted. And then what do? You run an axial T2 weighted FATSAT and you copy the exact location of those slices. So those two sets of slices, if they have the same matrix and slice thickness and slice location, have the exact same amount of frequency and phase and slice select information. All you've changed was which protons in that part of the body were in phase in the transverse plane when you collected the echo, which doesn't change the total number or shapes of the pixels, but rather only changes which ones are black, which ones are white, which ones are gray, and how they look, right? All of this phase encoding is only telling us where to put these pixels on our final image based off of where the anatomy was in the patient. What the actual picture ends up looking like, bright versus dark, so on and so forth, that was all done with TR and TE. So for instance, make sure I have this right here. If we look at these two, so here we have this axial of the ankle, right? And this is a proton density weighted axial of the ankle. This axial proton density FATSAT has the exact same slice position, the same frequency matrix, the same phase matrix, and the same field of view, which means that the strength of the phase encoding gradient, frequency encoding gradient, and slice select gradient were the exact same. Well, the phase changed, but they were the exact same between the two. But the images have different contrast because we changed TR and TE. These two different images have the exact same resolution and same gradient strengths repeated, but different TR and TE values. So here you can see it's proton density. Fat's kind of bright, everything's kind of bright. Hallmark of a proton density, everything's kind of gray. But then if you do the proton density FATSAT, the same exact parameters were used, which means that we have a different amount of contrast, but the exact same resolution. Right? Do the same thing looking at a coronal. There's a coronal. Same exact matrix, same exact everything, same exact slice position, but now instead of it being a coronal PD FATSAT, it's just a regular coronal PD. Right? Back to the FATSAT. So this is what's happening all the time when you have two images and you copy your slice location and your matrix is the same. Then the field of view is the same, matrix is the same, slice placement is the same. Then you have the same resolution. That doesn't mean you always have the same resolution. Sometimes you'll run a T1 at 256 by 256. Then you run a T2 at 224 by 224, even though you had the same field of view and same slice prescription. Okay. So each pixel location has its own unique pattern of frequency encoding and phase encoding, and there are differing amplitudes of signal at each of these differing pixel locations. The FFT allocates a tone on the grayscale from black to white and hundreds of shades of gray in between to each pixel, depending on the amplitude of signal within the unique pattern. All right. We'll take till the top of the hour, and then we will do time. We'll talk about acquisition time. Okay. Let's get back into this and talk about acquisition time. Okay. So we talk about all of these echoes. We talk about how long it takes to fill up case space with echoes. That's how long it takes for you to scan your patient. Once you put in all your parameters, set up all your slices, and you hit go, the computer will then calculate how long it's going to take for it to fill up all of the case spaces that you have for each. There's one case space per slice. For all the case space you have, how do we fill up all the case spaces? That's what time is. Once all the case space is filled up, scan's over. And that's why taking advantage of things like parallel imaging and stuff like that will lead to faster scans, which once again, we're going to come back into that more next week. All those little tips and tricks and all those little, not tips and tricks, but different parameters and options, imaging options we have to manipulate case space. So we're going to talk only about scan time equation in a conventional spin echo for this lecture. Right. As we introduce more pulse sequences in physics 2, we will introduce more time equations because different pulse sequences have additional parameters that change the time. Right. Fast spin echo has a different one. Gradient echo has a different one. 3D. So for the time equation for conventional spin echo, it is TR times phase matrix times the NSA. This determines, right, because the TR is how long it takes for me to collect one echo. The repetition time is the time from one excitation pulse to the next excitation pulse. So in that TR time period, in a conventional spin echo, I collect one echo. Phase matrix is the total number of echoes that need to be collected to fill case space. So to figure out how long it takes to scan a patient, I need to know how long does it take to get an echo and how many total echoes do I need. Those two things together tell me my scan time. On top of that, we also have the NSA, or number of signal averages, which is how many times we can repeat the entire process in order to increase our signal. One thing about noise being constant is that if we collect the same echo twice and put it into the same slot in case space twice, we will decrease the noise. Now, so when we look at case space, we said if we took this echo here and we put it into the wrong spot in case space, we would have motion artifact, right? But if we collect this exact echo 2 times and put both those echoes in the same spot in case space, the computer can then take an average and reduce the amount of noise. That's what NSA or averages or NEX, whatever you call it on whatever machine you're on, is doing. Instead of collecting all the echoes once, you collect all the echoes twice. That is because if we were to draw a picture of an echo, I'm going to do this laptop. Noise would look like a messed up part of the signal. When you collect an echo a second time, as we're putting that same line back into K space, the computer knows that there's some noise there. Oh, man. So what it can do is it can smooth out where the noise is a little bit more and then reduce the noise as I'm collecting that second echo. So every time I collect an echo and then I put that exact same echo back in the exact same line of K space, I can then reduce my noise. This is what we mean by an average. Because it collects the echo twice and it takes an average of the echo and generates a new echo with less signal, or with less noise. Sorry, with less noise. Now, if we were to collect that same echo and put it in a different spot in K-space, that would be motion artifact. But if we collect the exact same echo and put it in the same spot in K-space, we simply reduce noise. Right? And we do this all the time when we increase our NEX or NSA or averages, whatever it's called on your machine. But if I go collect every echo a second time, it's going to take me twice as long to scan, right? Because now I have to collect every echo twice. So I collected it once, then I got to go all the way back and collect them all again. Right. So repetition time is the time from excitation pulse to the next excitation pulse. In this time period, we collect one echo. It's a conventional spin echo. Right? It is measured in time, specifically milliseconds. Phase matrix, number of lines of K-space filled to complete the scan. As the phase matrix increases, the scan time also increases because it takes longer to fill K-space. So as we increase the phase matrix, we need more and more echoes. And the number of excitations. Right? Echo can be sampled more than once by maintaining the same slope of the phase encoding gradient over several TR instead of changing it every TR. Right? In other words, we collect the same echo and put it into the same line of K-space. The same line of K-space is filled several times so that each line contains more data than if data is only placed there once. So let's say you have a TR of 3,000 milliseconds. 3,000 milliseconds, if we convert it to seconds, is simply 3 seconds. And then we have a phase matrix of 256. That means every 3 seconds, I get one echo. How many times do I have to repeat that 3-second time period? 256 times. And if my NSA, if I said NSA equaling 1 means I'm only collecting all of the echoes once. NSA 2 means I'm collecting the echoes twice and putting them all in the same K-space. 3, so on and so forth. So if I'm only doing it once, then every 3 seconds I get one echo. And I need 256 echoes to fill up all the K-space. So I simply multiply 3 seconds times 256. That's how long my scan takes. Right? I get one echo every 3 seconds. I need 256 echoes. That's it. Right? 3 seconds go by, I get one echo. 3 more seconds go by, I get another echo, and so on and so forth. So during NSA, every data point is collected a second time, which allows us to average the signals, each acquisition, increasing signal while keeping the same amount of noise, or decreasing noise. You can put it either way. When you go from 1 NSA to 2 NSA, you increase your SNR by the square root of 2, or about 1.41. Next time you're scanning, you can see this. Pull out a sequence that only has one average NSA, NEX, whatever you want to call it. Then go from 1 to 2, and your SNR value will go from 1.0 to 1.41, or 100% to 141%, depending on which machine you're on, whether they use it as decimal or percentage. Right? But it doubles the scan time. This is because as we're collecting the second echo, we will also still collect some noise. So going from 1 signal average to 2 signal averages will not double our SNR. Because every time you collect those echoes, you're still getting some noise in there too. You're not getting rid of all the noise. Right? So if you increase, it'll increase by the square root of 2, which is 1.41. So if I go from 1 NSA to 2 NSA, then I will double the scan time of the pull sequence, and I will increase SNR by, say, 141%. Right? I'll increase it by 141%. I'll increase it by 41%. Right? It'll go from 100% to 141, or 1.0 to 1.41, depending on which manufacturer you're on, whether you use decimals or percentage. So, easiest way for us to remember this is simply to do the scan time equation. All right? Time equals TR times phase matrix times NSA. Multiply them all together, and that's going to tell you how long it's going to take to run your scan. All right? So, our first example. If you scan a patient with a TR of 3,000 a phase matrix of 256, and 1 NSA, what is the acquisition time? This is what questions on the quiz will look like. So you take time, which is 3,000 milliseconds times 256 times 1, which is 768,000 milliseconds. That will not be an option for an answer on the quiz, though, because the ART is going to expect for you to convert this back into minutes and seconds. And that's where things get a little tricky. You will have a calculator on the quiz that is built into Proctorio. You cannot use an outside calculator. There's one built. Why? Because that's how the ART does it. And you'll have a little calculator inside the program. You won't have a physical one. You'll have to click in the little calculator. Okay, so let's talk about how to change this into the correct answer. Step 1, you're going to have to convert it from milliseconds to seconds. You do this by simply dividing by 1,000. All right. So 768,000 milliseconds divided by 1,000 equals 768 seconds. All right. That's step 1. You have to convert it from milliseconds to seconds. Step 2. Now you have to convert seconds to minutes. To do that, you have to divide by 60 because there are 60 seconds in a minute. So if you take 768 seconds divided by 60 seconds, you get 12.8 minutes. This is the part that is a little confusing. 0.8 minutes does not equal 80 seconds because this is a decimal. And decimal numbers go up to 100, but seconds only go up to 60, right? So now you've got to convert the decimal 0.8 minutes into seconds. To do that, you take 0.8 minutes and multiply it by 60 seconds, 0.8 times 60, which gives you 48 seconds. So the correct answer would be 12 minutes and 48 seconds, not 12 minutes and 80 seconds. All right? I'm going to draw one out here all the way through, go through it, okay? So let's look at that. So I'm going to show you how these are going to look kind of on the final exam and on the quiz, right? You'll be given something like this. 1, scan 2. Scan 1 and scan 2. Scan 1 has a TR 600 milliseconds, ATE 10 milliseconds, a matrix of 256 times 128, right? A receiver bandwidth of 32 kilohertz, a slice thickness of 3 millimeters, a field of view of 15 centimeters by 15 centimeters, and 2 NSA. Use a different color over here. Scan 2 has a TR 3,000 milliseconds, a TE of 60 milliseconds, a matrix of 384 by 256, a receiver bandwidth of 16 kilohertz, a slice thickness of 2 millimeters, a field of view of 30 centimeters by 30 centimeters, and an NSA of 1. And the questions will be something like this. Which scan is faster? Or a question that says, or it'll just have scan times listed, right? And it'll also say something like, which scan has better resolution, which is what we talked about 2 weeks ago, right? The key here is you need to be able to look at all of this information that's being given to you, take out the information you need, put it into the appropriate equation, do the math to be able to answer the question, right? Because last week we talked about, or 2 weeks ago, we talked about resolution, right? Was that last week? That's 2 weeks ago. In which case, if you wanted to figure out the resolution answer, you would have to know the matrix and the field of view, right? And you'd have to know the matrix and the field of view. But if you want to know the time answer, then you need to know TR, not TE. TE doesn't matter for either one of these questions. You need to know the TR. You need to know only the phase matrix, not the frequency. And you need to know the NSA. TR, phase matrix, NSA. So you'll have these questions where it's just a dump of information, right? Neither of these questions has anything to do with slice thickness or receiver bandwidth, right? Neither one of the questions has anything to do with those, right? I'm not going to go back over the resolution one because we're already past 2 hours here, and last week's stuff, and we can go over that tutoring if anybody wants to, or final exam review. But let's do the math here and figure out which one of these scans is faster. Doing all this because this becomes a problem for some students all the way into physics 2. All right. So time equation, TR of 600 milliseconds times a phase matrix of 128 times 2 NSA. TR, phase matrix, NSA. Down here, we have 3,000 milliseconds times 256 times 1. Let's do the top one. So this equals exact same one we were just doing. Yeah. Equal 76,800 milliseconds. So now I convert. I divide by 1,000 in order to create seconds. 76.8 seconds. But there will never be an answer where the seconds, or there'll never be a correct answer, where the seconds are over 60. So here, you don't even have to do much math. You can just kind of figure it out. Well, there's 60 seconds in 1 minute. Take away 60 seconds, then it's 1 minute. And the remainder is 16.8, round up to 17. 1 minute and 17 seconds is how long this scan will take. Over here, we end up with, I'm going to change this just so it's not the exact same answer that was in the slides. We'll just change it to 2 NSA. 3,000 times 256 times 2 equals 1,536,000 milliseconds. Divide by 1,000 to convert to seconds. 1,536 seconds. Divide by 60 to figure out how many minutes that is. Now, you can just skip ahead and divide by 60,000. That's totally fine too. But if you want to skip a step, leads us to 25.6 minutes. But 0.6 minutes is not ever going to be part of the answer. It does include NSA. Oh, yeah, you're right. I did that math wrong. There we go. We switched those over. We changed this one to being 1 NSA. All was good. So then, now that we have 25 minutes as part of our final answer, this 0.6, we take 0.6 times 60 seconds. 0.6 minutes equal, I'm sorry. 0.6 minutes times 60 seconds. This gives us 36 seconds. So this answer is 25 minutes and 36 seconds. All right. So step 1 is to memorize the time equation. Where students will get mixed up. Just telling you that the typical things I see with students getting mixed up. They will use TE instead of TR, and they will use the frequency matrix instead of the phase matrix, right? Make sure you understand it's TR and phase matrix, not TE and frequency matrix. That's why you want to memorize the time equation. TR times phase matrix times NSA. All right. And the other thing here is then the conversion. 76.8 seconds is not ever going to be the correct answer. You have to convert it to minutes, right? 0.8, and then we come down here. 0.6 minutes is not the same as 60 seconds, right? It's not the same as 60 seconds. You have to convert that over. All right. Now, none of the questions will be based on rounding errors, right? In other words, you'll never have a question where it's like 4 minutes and 16 seconds or 4 minutes and 17 seconds, where a rounding error will give you the wrong answer, because that's just too much math for me, right? You may have a question, though. For instance, here, if this is the correct answer, one of your options will be 25.6 minutes or 25 minutes and 36 seconds. This is the correct answer. This is not. The other thing you'll have is you'll have an answer to say 25 minutes and 60 seconds. This will not be an option. You will not have that decimal as an option. But you will have as an option 25 minutes and 60 seconds. But 25.6 does not equal 2 minutes and 60 seconds. 0.6 minutes is not the same as 60 seconds. All right? So usually converting this decimal is where students make a mistake, or they make a mistake by not getting the proper information out in the first place. All right? You'll be given lots of questions like this on the registry. The registry likes to spit out something like this and then ask you a whole bunch of questions. Which sequence is faster? Which one has better resolution? Which one is T1 weighted? Right? All of these questions like that. All right. So that's why we're practicing those now. Make sure you read the question, especially when it comes to the final. Is the question asking you about resolution, or is it asking you about time? Because you may have two sequences, one that's faster with worse resolution. And so if you think it's a question about resolution, you'll choose the wrong one, even if you do the math right. If you have a question that's actually about time and not resolution, you may get that wrong too. So make sure you are paying attention to what the question is asking, and you're looking through all the information that's given. You got to get in this habit now, because you're getting very close to the registry, of getting a bunch of information, pulling out what you need, and ignoring everything else. All right? Because they'll just information dump. Here's all the information you could possibly know about a pull sequence. Tell me how fast it goes. Tell me what its resolution is. Tell me what its weighting is. Right? All those things. Okay. Okay, so time parameters. There's a scan time equation. TR increases, scan time increases, so does SNR. Increase the phase matrix gives us an increase of time and decreases SNR and affects resolution. increase in SA, increases time, increase of SNR. And this is once again why a lot of techs like to decrease their phase matrix, because as you decrease your phase matrix, you decrease time, which is good, and you increase SNR, which is good. The only thing is, it's at the cost of resolution. Like I said, some techs scan that way, some do not. Okay, so these are the time parameter questions. You're going to see regular parameter questions on this quiz too. This parameter goes up, what happens to time? Right? This parameter goes down, what happens to time? If it's not part of the scan time equation, it does not affect time. Right? TE doesn't affect time. Frequency matrix doesn't affect time. Slice thickness doesn't affect time. Right? Receiver bandwidth doesn't affect time. It will in a fast spin echo, and we'll talk about that in a fast spin echo lecture in physics 2, but we're not there yet. Right? Receiver bandwidth is very weird in a fast spin echo, but we'll get to that, like I said, in physics 2. Okay, so any questions on any of the stuff we've gone over today? Anything at all? I know it was a lot. I promise you, next week, we will not be going over 2 hours. It will not be nearly as intense. Next week will feel like a breath of fresh air because we will just be talking about the different stuff. And then we go into the final, and then we're into physics 2. I'm going to open up. There is an exit ticket. I know these last 4 weeks have been grueling for this class, and I appreciate everybody sticking around for it. I know that it is a lot. But the good news is we are through the woods. Hopefully you will not find next week nearly as intense. Definitely won't be as long. And then we're into the final and we're done with this class. Okay, exit tickets are open. When you are done with your exit tickets, feel free to log off. And there is a time question. There is a time question for the calculations in the exit ticket, right? So you can start to get an idea of that. All right. I'll hang around for a couple minutes. If anybody wants to hang around for tutoring or has any questions, I'll be back in about 10 minutes. Otherwise, whenever you're done with the exit ticket, you're good to go. And I will see y'all next week. Yeah, you had a question, Omar?
Oh, hey, Kevin. Yeah, it was just about last week's material, just about some slides, if that's okay.
Yeah.
It was one of the slide 23 from last week's encoding
Let me
class.
pull it up real quick. Coding. 23. Yes. All right, I'm on there. Which one is it?
So I know that like last time in tutoring, you were telling me how the received bandwidth doesn't like change the frequency field of view, how they're related, but they don't change each other. But this slide was saying how if you increase the frequency field of view, that's going to increase the received bandwidth. So it kind of words it like it does change it. So I was just trying to get some clarity on that pretty much.
That's going to be vendor specific. That's going to be vendor specific. So that's why it says it in there.
Oh, okay,
On a
okay.
GE, that is true. On a Siemens, that is not, because of the way that they change it based off of whether you're changing the bandwidth. So I guess what it should be saying there, let's see, increasing the frequency field of view increases the received bandwidth. It increases, would actually decrease the received bandwidth per one. Yeah. So that's going to be a vendor specific issue. That would be describing a GE right there.
Oh,
Because
okay,
with
okay.
them, you measure the bandwidth across the entire field of view, right? The bandwidth is measured across the entire field of view. But in a Siemens, it's by pixel. So you may make the pixel bigger, but it has the same amount of frequencies per pixel. Where on a GE, when you make your field of view bigger, it's actually more of the echo that you're collecting.
Oh, okay.
So, yeah.
Okay. And for the ART, like it won't have any questions like this then since it's vendor
Oh, God, no.
specific. Yeah. Oh,
No.
okay, okay. Gotcha,
We
gotcha.
go way more into depth than you need for the ART. Because the idea is like, if you barely pass all of your classes here, you get a C in every class, like you score 75 and barely pass the program, you're still going to pass the ART because our material is way harder than the ARTs. So a lot of this is to help just get you to understand the stuff. And like, if you look at the quiz, like there was no quiz questions that were getting that far into it. So no, I would not in any way, shape or form worry about that for the ART.
Oh, okay, okay. Sounds
Yeah.
good.
Yeah. It's
Okay.
one of those things that we go deeper than the ART needs us to, just because it's, you teach too much, you make sure that the people who didn't understand everything are still going to pass the ART. Because if you can't pass the ART, and that's my philosophy, at least with my class. If you can pass my class but you fail the ART, I haven't done my job. So we teach to a higher level than what you really need to know for the ART.
Gotcha, gotcha.
Yeah.
Okay. Thank you, Kevin. I had another question, but I think Mary has her hand, so I don't know
Oh
if
yeah. What's up,
yeah.
Mary? What's your question? You're on mute, Mary.
I'm having a hard time trying to figure out how to figure out the phase and frequency direction when it's a square field of view. And I know anatomy has something to do with it, and I was wondering if you could help explain that.
Do you mean like which way you would choose for it to be?
Yeah, and it's all coming from watching the text decide quickly to swap phase and the phase direction.
That's
So
just
I'm like,
usually wrap.
yeah. So I know
Not
why they're
artifact.
doing it, but I'm like, they can quickly like decide like, okay, that's the phase direction, and that's the frequency direction. Like they just see it so quickly, and they say it's dependent on the anatomy. But if it's a square field of view, because I've been going off of like what's the longer axis and the shorter axis, but I'm still having like a hard. I'm kind of wanting an example maybe, because you explain things a lot better than when we're out there.
What type of machine are you scanning on?
A GE, all different types of GE.
Gotcha. Let's pull up a brain.
And I'm kind of like wanting to, from this, give myself homework So if you're looking things up, I'm kind of curious how you're doing it. So I
I'm
can.
just pulling up an MR image to show it to you.
Okay.
Okay. So the main reason why we would care about frequency field of view versus phase field of view is usually time. And you're right. Smaller field of view will be phase because phase takes time. Phase is part of the time equation. Frequency isn't, right? But if you have a square field of view, it doesn't matter. So now it's a question of any artifact that goes in the phase encoding direction, which mainly we're worried about motion and wrap. All right. So here, the tip of the nose is wrapping here.
Yeah.
So when I look at this image, wrap occurs when you have anatomy that is outside of the field of view, but inside the coil.
Yes.
Okay. So if I change my field of view this direction, then any of the information of this patient's shoulder was going to wrap to the top if this was the phase direction. But out here, there's nothing. And out here, there's nothing. So that's going to be my phase direction.
Okay.
Let's look at some other images. So when you're looking at it, all you're looking at is, okay, what is sticking out of my field of view that is still in my coil, right? Because if there's something that's out of the field of view that's inside the coil, wrap will happen, and it'll only happen in this phase.
Yeah, it happens so badly with ankle or foot. So
yeah, here, let's look at those. And one of the big problems with the ankle and the foot is that the other ankle or foot that's in the machine is still producing signal because it's still in the same plane. If I have 2 feet right here and I'm doing an axial and I have 1 foot over here, everything in the axial across that entire gradient gets excited. So you're exciting both feet at the same time. And if that coil is super sensitive, it'll pick up the signal that's even outside the coil, which is the very annoying thing with using a foot coil.
Yeah.
That's why what you usually do is you have the foot you're looking at in the middle of the magnet and then take the patient's other foot and get it as far away from the coil as possible.
Yeah, but then you still have
put it up against.
You still have the toe of the anatomy and interest sticking straight into the heel.
Yep, you still have the, exactly. Let's pull up this. So if I'm looking at axial of the foot, right, this is an ankle, right? Well, there's no anatomy out here, and there's no anatomy out here, so this is my phase direction, so there's no wrap. If this was my phase direction, then the top of the foot would wrap here. So this has to be frequency, and this has to be phase.
Yeah.
Otherwise, I get wrap.
And I'm thinking that has to be frequency just because it's the long axis.
Which is true, too. But here, let's take a look at a sagittal, which is a square, right? Because now here we have the problem.
Yeah.
If this is the phase encoding direction, then the toes can wrap. If this is the phase encoding direction, the top of the leg can wrap.
Okay.
So here, you're going to have to use phase over sampling or no phase wrap.
No phase wrap. Is that why I see no toes shoving into the heel here? Or is it because they swapped the phase and frequency direction?
Well, if you swap the phase and frequency, whatever was up here outside the coil would be wrapped down here.
Oh.
This way, you can't get rid of wrap by changing the phase and frequency. You've got to use
no phase wrap, oversampling.
Yeah, no phase wrap. Which oversampling is the technical name for no phase wrap.
Oh, and I thought the point of swapping the phase and frequency is to help get rid of wrap.
It is, but here you can't. Here you have anatomy outside the field of view that's inside the coil.
In both directions.
In both directions.
Okay.
So in both directions. So you kind of get stuck here where you've got to then figure out what's going to happen. And in reality, the coil only goes so far up on the foot here. Another thing you could do is just make your field of view bigger so that it included all the anatomy in the coil up here and then make that your phase direction, and then you wouldn't get wrap in your frequency.
Okay.
Let me see if I can.
We're going to wrap in both directions. Okay.
Yeah, so that's why axial ankles can be so difficult. But if we go look at the coronal ankle, the coronal ankle would load. Thank you. Then once again, it becomes an easy decision. Phase direction because there's no wrap. But this is where ankles get difficult Because if the other foot is right here and it's too close to the coil, it will wrap into it because the coil will pick it up, even though it's not in the coil. That's why you have the patient put their other foot as far away as possible.
Okay.
Yeah.
Okay.
Whenever I have a patient that does a foot, I try to get the foot that we're looking at in isocenter, and I say, take your other foot and put it as far away as possible. Don't touch the side of the machine, but very close to it. And usually put a pad between their other foot and the machine, so you're not going to get any burns, any RF burns from that. And then that way you can help reduce that kind of wrap.
Okay.
And then, yeah.
Okay.
But most of the time, that's the reason. Now, it's also motion. Motion also goes in the phase and frequency direction. So another example of that would be,
like flow motion.
exactly, like in a cervical spine.
Oh, cervical. Oh.
Yeah, let me open up a cervical spine here. Oh my God, this takes forever to load.
This also seems to explain why another tech I saw, when he does tib fib, he'll lift the other leg up higher.
Exactly.
To get
it out of the way.
As far
Can't
as
wrap.
it can. Yeah.
So here, we have another example where we have the face coming out of this side of the coil, right? It's still close to the coil because it's a spine coil. And then we have here as well. So in here, we use a sat band to get rid of this signal. And then we also use no phase wrap, but then the carotid blood flow comes up this way, right?
Yes.
Well,
Which
if the
is
phase
the
direction
frequency
is going
direction
back,
here?
what's that?
Which is the frequency direction here?
In this case, frequency is anterior to posterior.
Ah, see, this is
Because if phase was anterior to posterior, then the carotid flow motion artifact would go into the spinal cord.
Oh, okay.
So you can get motion artifact. You can control where motion is going, or you can control where wrap is going. And there's other artifacts too, but I mean, motion and wrap those are by far the most common artifacts that we see most of the time, and they both go in the phase direction.
Gosh, I wish I just had like a booklet of practice images to figure this out all day.
All right, let's see.
And I know, I don't know if Omar's still on here. I know he had another question, but like this is giving me good basis for practice.
I can wait. No worries.
Well, I know we got class in 8 minutes.
So here is a case where there's flow motion. I don't know how well you can see that. It's not like the most worst flow motion. There's flow motion going across the spine. I don't think it's going to show up too well through Google Meet stuff, though. That's Gibbs. That's not motion. Oh, there we go. That one's. Let's see if I can make this one bigger. Ugh. Really? Stupid researchers. Anyways, this one has a bunch of carotid motion that gets into the spine and makes it look like there's a infection there.
Oh.
Yeah. This tends to happen.
To fix that, it's not that we just use no phase wrap. Like we can swap.
You can swap it, and then the carotid, instead of going this way, will go up and down where it won't be in your part anymore.
Yeah. Okay.
But an even easier fix here is just put a sat band and saturate the flow signal. Yeah. You can easily take care of this with a sat band. Just put a sat band inferior, the blood will become saturated, and then it won't have any signal, so it won't be an artifact.
Okay. And that also explains why they don't have to worry about swapping all the time. They have options. Okay.
Exactly. And usually what happens is like you have a patient who's got like, I mean, I've worked with radiologists who are extremely particular about their field of view. They're like, don't ever make your field of view bigger. And then you get a patient who has larger anatomy for whatever reason. And then it's like, well, I wasn't worried about wrap, but now this patient's face is like, you've got some patient who's like 6'8", a 6'8" person with a huge head. And now because you can't change your field of view, so much of the nose is wrapping to the back, it's now in the part. Now it's like, okay, well, now I have a problem because this radiologist doesn't want me to increase my field of view. And increasing your field of view also decreases resolution.
And would no phase wrap be your first option
Yeah.
in that case?
Yes.
And that messes with, but that messes with something with the image, doesn't it? Doesn't it, or this maybe the
On a GD,
time?
it prevents you from using a rectangular field of view.
Oh, okay. Yeah, see, everything has a cause and effect. Okay.
And on Siemens, it costs you time. On
Okay.
Siemens, you use something called phase oversampling.
Okay.
It's like how you deal with wrap on different vendors is one of the biggest differences between vendors. Yeah.
Okay. So this is going to be a learn as I go thing. Okay.
Yeah. But more likely than not, I would assume they're looking at the anatomy and they're looking to see if there's wrap. That would be my guess.
Okay.
Unless there was motion. But most of the time there's motion. You're talking about flow motion usually, unless the patient's moving, in which case flopping it's not going to do anything for you. But if it's flow motion, just use a sat band. So I would imagine wrap is probably the reason they're looking at that. And they're just looking at the field of view. Which one is coming out? Like, oh, there's stuff sticking out those. I'm going to get wrapped there. I got to swap that or something.
Okay. All right. Thank you.
Yeah. Do you have another question, Omar? Maybe I can answer in 5 minutes. I know you got another class.
Yeah. Well, I did have some other ones, but I can hold it for another time. I guess I just had a question regarding or yesterday's quiz.
Okay.
There was a question that talked about sampling time, and I went through the slides, and I know that it talked about sampling window, and it talked about sampling rate, but never sampling time.
I'll go back and give everybody credit. The registry used to call it sampling time, and then they changed it to sampling window. And I went and corrected in the webinar. I must have missed fixing it on the quiz. Because like every year, the registry puts out their new like study guide, basically. And I always make my stuff match what's on the ART study guide. And they call it sampling time, and they changed it to window. So I changed it in all the slides. I thought I changed it everywhere. I must not have changed it on the quiz. So yeah, I'll give everybody credit for that. But it is the exact same thing. A sampling time, sampling window, sampling time is the same.
Gotcha.
But once again, it's the registry updating their stuff and me missing that. I thought I'd fixed all of it. I had to go through the whole lecture and like make sure everywhere it said sampling time, I changed it to window. Must have missed it there. Window.
Okay.
Yeah, sampling time is equal to the duration of the readout. It should say sampling window is equal to the duration of the readout grading.
Gotcha. Okay. I was just wondering that then. Thanks, Kevin.
Yeah, not a problem.
Yeah. And do you do tutoring on Fridays too, or just Tuesdays? Just for the future?
Yes. Yeah, if you here, let me pull it up. Yeah, I do. It's got to be kind of in the morning because I have a webinar. So from 7 to 11. Although I have one student right now, I meet at 8.
Oh, okay.
So yeah.
Gotcha. Okay. Sounds good. And only physics, right? Like no safety stuff, right? If we did.
I don't
Yeah.
I don't have access to the safety course. I mean, I'm an
Okay.
MRSO, so I have no problem talking about safety stuff.
Oh,
but
okay.
Like, if you ask me like what's on a quiz or a PowerPoint, I don't have access to it. But we can talk about it whenever you want.
Sounds good. Thank you then. All right. See ya.
Yeah. Jillian, do you have a question?
Yeah, I just also had a question about the last quiz. I saw a couple times there was a term that said readout. I think I was confused on like what that actually meant, and I went back and looked, and I see it mentioned once on the slides. But I don't understand what it means.
It is the same thing as the frequency encoding gradient. It's a different name for the frequency encoding. When we're talking about sampling, we use the term readout gradient.
So it's just this like sampling time then, or sampling window, or is it gradient?
It is the readout. It is the frequency encoding gradient.
Which
it is the wonderful part of MRI where we have 5 names for the same thing.
Okay.
Let me open it up. Let me pull it up real quick. That is all it is.
Which I don't remember what the questions were, because I think when I was reading the questions, I was just confused. So I wanted to remind myself to look it up afterwards. But what does that mean then also?
What's that?
So then what?
The frequency encoding gradient is called the readout gradient or measurement gradient.
Yeah.
Those are all the same name for the same thing.
Okay.
So if we look at like let me pull up in the quiz. I can't share it because we're recording, but yeah, like the sampling window is the duration of the readout gradient. So the duration of the frequency encoding gradient, same thing.
So duration. Okay.
Yeah.
Okay.
Is that the sampling time one, which I'm going to give everybody credit for, also says duration of the readout gradient, which is true, but so it does say sampling time there. But yeah, the readout gradient is the exact same thing as the frequency encoding gradient. It's just we use the term readout when we're talking about sampling the echo, and the rest of the time we call it frequency encoding.
Okay.
So yeah.
Okay, I was just like a little confused. I saw that a couple times on the quiz, and I was like, I don't know.
Yeah. It's a readout
Okay.
gradient, frequency encoding gradient, same thing.
It's the same thing. Okay,
Yeah.
perfect. Thank
Okay.
you.
Yeah, not a problem.
Appreciate it.